I've had some issues with these little adapters for these projectors for whatever reason. They, I've got 3 of them. I went and bought 2 of them over the weekend at there, and certain rooms, some of my adapters won't work. They all work at my desktop at there. So this one seems to work everywhere. So this was the one on my desktop. Well, at there. Okay, I don't think I finished chapter 2 slides. However, what was important in chapter 2 is repeated in chapter 3, so I can go ahead and just move on to the next chapter here. Right there. And this is getting into structured program development in C. That there. And this is really a key chapter. This one here talks about the problem-solving techniques. This is a chapter that I consider very important because you're supposed to become engineers. And engineers, by definition, are problem solvers. The job of an engineer is to take current technology and adapt it to problems and solve current problems. They can be problems in terms of power distribution. That's there. And here's the rest of our crew sneaking in here. Right there. Right there. Or it can be solving problems on a manufacturing floor. It can be solving problems in terms of power outages in buildings. Why transformers tend to blow. Right there. It can be solving problems such as how to feed a population. But the job of an engineer is to take existing technologies or what tools you have in hand and solve problems right there. And that's what computer programming is about to a degree. Not there, I'm sorry, but as I go over, I can see all the guys, but there. Actually, give a choice, I take all the projectors at there. I like to see faces when I look around the room. That there. So, okay. That there. So we're going to develop algorithms. Now, the algorithm is basically the problem-solving technique that there we're going to use. How does our program function? And as we look at our algorithms, we have a series of tools on how we're going to write them. Remember, a computer program is like a cookbook right there, or a set of instructions. Now, many of these instructions are ones where we grab a piece of data, we process it, then we grab the next piece of data and we process it. Or we go through a list and we add up all the various things up there. So we're going to be looking at the if and the if else. We're going to look at the while. We're going to be looking at the for loop. And we're going to start looking at there. So there's a lot in this chapter. So we'll probably talk about this chapter today and Friday to an extent right there. So again, this just repeats the chapter outline right there. So okay, number 1. This is the key thing that a lot of students have trouble with, and that is the concept before you can solve a problem, you have to understand the problem. What is the problem? And I'm going to take this beyond writing computer programs. And again, Mr. Decto and his son are computer science types. They're not engineers. But his dad might have been a computer engineer. I'm not sure. His son is definitely a computer science graduate. But again, engineers and computer science types, that they're, before you can solve a problem, you have to be able to solve it, come up, figure out what the solution is. Before you do that, you have to understand what is the problem. Sometimes that's the hardest part. What is the problem? That there. The old joke is, a friend of mine went through 5 marriages. He'd been divorced 5 times. He was single at the time. What was the problem? Obviously he had a problem, there. And before we could solve it, we had to determine what the problem was. So understanding the problem. Why does your car keep going through tires? that there. Is it the way you drive? Is it the alignment of the car? Is it the brand of tire you're buying? That there. What is the problem? That's, and the key thing when we're solving problems from an engineering standpoint, we're looking for a root cause. So writing a program, how do we solve, what is the problem? What is our program supposed to do right there? Now, if you're writing an embedded program, our program is supposed to operate a petrol pump. So what are the steps that have to be done for it to operate a petrol pump? We break it up quite often into smaller problems right there. If you look at a petrol pump, it has multiple functions, right? One function is to pump petrol. So you would write a routine that will pump the petrol, check the maximum amount of petrol it's supposed to pump, and in that case, you're, say you walk up to the window and hand the clerk behind the window 50 ringgits, she sets 50 ringgits on the petrol pump, and once you get to 50 ringgits, you're supposed to stop pumping petrol. That's what the person paid for, right? But then you also need to check to make sure that you haven't hit the overflow trip right there. Otherwise, you end up with petrol all over the ground. You have to check to see if there's petrol in the tank right there. You have to check to see whether the nozzle is in the automobile or motorcycle petrol tank. There. So you have all kinds of things you have to check. And you have to make a list of those right there as we write our program. So, again, that goes back to we must have a thorough understanding of the problem and a carefully planned solution approach. So before we can start pumping the petrol, we have to list all the various things we have to do before the petrol is pumped right there. So we're going to go through that with some examples there. So there's 2 chapters discussing the techniques to facilitate the development of structured computer programming. So actually, the chapters 3 and 4 are the heart of this course, actually. An algorithm is a series of instructions. It's the recipe. It's the step-by-step that we go through. So you've got 2 things. One is the algorithm, and then the other is writing the program. Writing the program is the easy part. Developing the algorithm is the difficult part. I could write code all day long if you give me algorithms, and I could write it in 15 different languages, given a syntax guide for each of the languages. I may make a lot of mistakes, but specifying the order in which we do things and all the various conditions is the hard part, right there. So, just like writing the manual on how to replace the engine of a, Perodua MyV. How do I take the engine out and put a new one in? It's easy to take the engine out and put a new one in if someone's outlined the steps one by one for you directly. Now, once somebody wrote down the steps one by one, the next part of creating a program to do that is to clean up the English or the Malay and make it read properly. But a skilled mechanic has to write down the steps. And normally he would write down the steps as he's actually taking an engine out right there. Sometimes if I'm going to be writing a instruction manual for something, and I've done that, I will actually watch somebody do the operation and write down every step they do as they do it. One of the things in my house is I cook Western food, but I'm terrible about writing down recipes. I am terrible about writing down recipes. And when my wife first moved in with me after we were married, she wanted to cook the things that I cooked or learn how to cook the Western food. She would actually follow me into the kitchen and write down everything I did. And she's got in her computer recipes for Western style baked beans, and she's got down, I put 3 tablespoons of barbecue sauce, 1 teaspoon of chili flakes, ground beef, I put half a pound of ground beef in there with it. I mean, everything that I put in a style, I don't, should I say what's the right word for it? Well, whatever I put into a baked beans, whatever pot I'm going to make a pot of baked beans. Whatever I put into it, she wrote that down because I just walk over to the refrigerator, grab my mustard, and squeeze it into the pot. I have no idea how much I'm putting in there. Sat there. So, there. And, if she's going to duplicate that, she has to have an idea how much. So she would put down 3 tablespoons or 2 tablespoons. Sat there. Unfortunately, ladies, your mother probably cooks the same way, right? They don't have recipes. Sat there. Your mother cooks nasi lemak. Does she measure how much coconut milk she puts in? No, she just puts it in until it looks right? Well, that's the way I cook Western food. But if you don't know how to cook Western food, you need a detailed recipe to do so. And remember, you're writing instructions for a computer. It's dumber than your 12-year-old little sister. That there. You're trying to teach your 12-year-old little sister how to make a beef burger, for example. That there. You got to give her very detailed instructions. That there. Maybe not your 12-year-old, 9-year-old sister. That there. So these instructions are called the algorithm. Correctly specifying the order in which the actions are taken is important. Remove engine mount bolts. Remove engine. How about if we put down remove engine and then remove the engine mount bolts? What happens when we put that chain on the engine and start lifting it out of the car and we haven't removed the bolts? That there. Bad things happen, right? That there. So it's one of those cases where you have to think about this a little bit. Oh, that there. There's a radio show in the U.S. called Click and Clack, Car Talk Guys, and they talk about one guy that decided he wanted to remove the engine on a car. So what he did was, instead of putting the jack on the engine, he put the jack, he hooked a crane up to the car, crawled under the car, unbolted the engine, and then he lifted the car up and left the engine hanging. That there. So, out there. So, and then he brought the truck in, and then he dropped the car down. I don't know what he did with the car, but someone did it reverse, right there. So there are, the order in which we do things is important, right there. Just like, if you're going to bake a cake, one of the first instructions is, and this is Western cake baking, is you preheat the oven to 200 degrees Celsius, for example, or 170. That's there. You don't place the cake in the oven and then bake for 30 minutes and then come back and turn the oven off while it's been sitting in the empty oven with the heat turned off. You have to turn the oven on before you put the oven into the cake. Right. If you're going to make donuts, you have to put the yeast in before you allow it to rise. The order in which we do things is important. Right there. So consider the rise and shine. There. This is senior executive. Get out of bed, take off pajamas, take a shower, get dressed, eat breakfast, a carpool to work. Well, that's an interesting set of instructions. What happens if he forgets step number 4 until after 6? In other words, he goes out after he takes his shower and gets in the carpool butt naked. His coworkers might have a shock right there. So, suppose or perform slightly different order. Get out of bed, take off pajamas, get dressed, take a shower. All right. In this particular case, he's going to take a shower with his work clothes on. I think it'd be more humorous than if he forgot to put his clothes on. But regardless, the order is important right there. Pseudocode is something that people write out their programs in instructions that look a little bit like English, but they're not quite English, and they're not quite C. You don't care about the syntax. I write a lot of pseudocode. 90% of what I write is pseudocode. So when you write pseudocode, is basically the way that you write the algorithm And then the last step is you take the pseudocode and you apply the syntax of whatever language you're applying, and that becomes your code. You formalize it right there. So you conveniently type it into a computer using any editor program. Carefully prepared pseudocode code may be converted easily into C. If you did your pseudocode right, all you do is just change the instructions into C statements right there. You may have to add 4 or 5 statements for one statement. Pseudocode might be input number 1. Well, in input number 1, I might have to do a printf to print the prompt, and then do a scanf. So my pseudocode might just say input first number right there. So definitions are not executable right there. And I can't breathe again. So a definition here is we're just defining I as an integer is what we're talking about. Some programmers choose to list each variable and briefly mention the purpose at the beginning of the pseudocode program. Now this is, what he's talking about here is we're writing pseudocode, but if you notice that the pseudocode here looks just like C. This particular programmer that's writing the pseudocode actually writes pseudocode that looks like the programming language right there. Now when you write pseudocode, and you're defining variables, and what did I do with my pen? There it is, right there. What he's saying there is that int I, right there, there, and I may put a comment here. I is the loop counter, right there. Is what he's saying right there. And as I write the pseudocode, I'm saying what does I represent right there. So, that there, by definition, that there. So, if you use variable names, and I talked about variable names before, right? Where I said that you would use variable names that would represent something that means something. That little comment really isn't necessary right there. So, normally programs are executed one after another. It's called sequential action. C is one of these programming languages that does everything sequentially. Not in our program. If I was teaching the digital course, I would be teaching some VHDL as part of the digital course, but Dr. Lillick teaches the digital course, and she doesn't use VHDL in that course. But there's a language out there called VHDL, and VHDL or Verilog, right there. These are 2 hardware description languages that they're not computer programming languages. They're used to design digital hardware, right there. VHDL is more of an American language. That's the one I teach because I know it, and I've done a lot of work with VHDL. And you've heard me mention VHDL before as one of the languages that I confuse syntax with. Verilog does the same thing, only it's more used in more commercial applications. These languages allow something called concurrent program design, where you have three different processes happening at the same time, right there. Now, in order for that to happen, we have hardware that does this one, hardware that does this one, and hardware that does this one. But VHDL and Verilog are hardware design languages. So we're designing the hardware so we can tell it we want these three things to happen at the same time. C is a computer programming language. Computer programming languages means that the microprocessor has got to go get the instruction from memory, look at the instruction, determine what to get for the next memory, and then go get that, go get the next thing, add the two, multiply the two, whatever, within the register set, and then go on to the next instruction. So microprocessors, by definition, can only do one thing at a time. Right there. VHDL, you're designing custom digital hardware. It can do 20 different things at the same time. Right there. It just requires more hardware. Right there. So by definition of this being a computer programming language, everything is done sequentially, one line at a time. Right there. Now, normally they're in the order which we put them in. Now, later in this chapter, we'll look at transfer control, where we can do call a function. When we call a function, instead of going through here, we're doing one line at a time. We're doing this line, this line, this line, this line. And then we do a printf, for example. Printf is a function call. That tells it to go over here, run the instructions for printf, and when it's done, go back and start executing the lines after that. Then we hit another function call here called square root, right there, and we go off and we do the square root function, and then we return back right there. These are transfer of control functions where we go off and do something else. We could do a while here, while. We'll talk about the while statement here in a few. And we can have some instructions here. We get to the end of this instruction, we go back to the top. And we just keep doing this over and over again until this condition is false. And we'll talk about that then. We can do an if. We've done an if. We have a condition. If this is true, right here, we execute these instructions. Otherwise, we skip them. So these instructions here are only done if this condition is true, and we'll talk about that there. So these are program control structures right there. So we'll be talking about that within the next 30 minutes. Actually, we'll introduce a few of those right there. So in the 1960s, it became clear that indiscriminate use of controls was the root of great difficulty. Well, I'm glad he didn't say the root of all evil. There's a saying in English, I don't know if it's in ways, it says money is the root of all evil, but right there. But in programming, we used to have something called a go-to 340, which is this is a line number right there. We usually use line numbers right there. And we would have a go-to right there. And then down here we would have the code, and we would have another go-to. And this would create what was called, the term that they used to use was spaghetti code, because your code went all over the place right there. It became very difficult to debug and troubleshoot, and right there. So as a result, the go-to is almost never used anymore. It still exists in the programming language. You can put a go-to statement in there, but nobody teaches how to use the go-to statement right there. It used to be a very common thing out there, but right there. So the finger, he talks about the go-to statement right there. The finger of the blame was pointed to the go-to statement, which allows you to specify control as one of many possible destinations. Structured programming became almost synonymous with the go-to elimination. So I didn't look at these slides ahead of time. I just kind of go through the headings and I talk to them the way I would if I was writing the slides. So sometimes I need to get there. Research has demonstrated that programs can be written without any go-to statements. The challenge of the era was for programmers to shift their styles to go-to less programming. Now, as I said, almost nobody teaches how to use the go-to statement, and I'm not going to teach how to use the go-to statement. But the results were impressive. Software groups reported reduced development time and more frequent on-time delivery of systems. In other words, it worked. If we make the go-to statement go away, right there, we tell the go-to statement to go to hell, that there, people wrote better code. We took away something that made writing code easier at the time you're writing it, but it created huge problems. The go-to statement actually was replaced with a call statement or a statement or function calls or procedure calls, where if you're say rebuilding the engine of a car, for example, and one of the things that you want to do is replace head gasket. That's one of the functions that they're, and in your top level program, you would say remove engine. Well, you wouldn't put all the instructions on how to remove the engine right there. You would have a chapter in your book on how to remove the engine. So the person who's removing the engine would go through and say remove engine. They would go to that section of the book and they would remove the engine. Once they were done removing the engine, they would go back to the to the main program or the main set of instructions, and the next thing says remove head gasket. So then you would go to the section on how to remove the head gasket, right there, and then you would go back and then say clean heads properly, and then you'd go to the section. So every little section was written into a function on its own, right there, and that's called top-down programming. So the go-to used to be go to remove engine, and at the end of the remove engine, go to remove head, right there, and you'd have all these go-tos. Instead of the go-tos, you would have a top-level program that would outline the steps right there. One of the things that I like to cook is called a chimichanga. It's a Mexican dish, which is basically a type of, it uses a tortilla which is a real thin naan. It's very similar to naan, only it's very thin, and it's not crispy like roti canai. It's flexible like Indian naan, but and you can buy it at the store. They call it, I think Mission sells it. They used to call it roti tortilla, but now they just call it original blend. They remove the word tortilla because nobody knows what a tortilla shell is right there. But regardless, and if you look at some of the cookbooks that are in ebook form, they'll give a hyperlink on how to make the tortilla. Not there. So the recipe calls for 8 to 10 8-inch tortilla shells. Well, there's a little go-to, a little call where I could go back and get the rest, and make those if I did buy them. I typically buy them. In the U.S., you can buy them at any of the Mexican grocery stores for like 3 cents a piece. Only an idiot would make them themselves, or a real connoisseur, right there. But regardless, we would have these function go-tos on that there, or not these go-tos, these calls right there. So, and there. Okay, well, instructed otherwise, one after another. At there, the flow chart is basically a different way. Flow charts are graphical at representations of programs, and I'm not going to draw a flow chart because he uses them right there. Here is add, grade a total, add 1. If you have a diamond, that's a decision making. If he shows a loop, usually with a diamond on the top, but at there. But he's got, okay. This particular author did not do what I thought he would do. Quite often in flowcharts, what you will see is something that looks like this. This is an if then else. This is false or true. It does this. And it has some blocks here. False, it skips over it and does out there. This joins back into this box here, and we have this graphical representation right there. Very few people use flowcharts anymore. Back in my first programming class, and I think it was only my first programming class, I was required to buy a little plastic temple with all the diamonds and squares, circles and ovals and all the shapes that you would draw flowcharts with. And every program we wrote, we would have to include a flowchart with it, right there. those were back in the days where we had punch cards, and writing code was a very painful experience, to say the least. Our code was very long and drawn out there, and if we made a mistake, meant going through and waiting another half hour to get to a key punch machine. Well, actually, once we submitted the code, we waited a half hour to get the results, and then we waited for a key punch machine. Then we we fixed our mistakes out there. Each card was a line of code right there. And normally you pre-wrote your cards on a big green tablet that there where you wrote each line of code that there, and then you went over the key punch machine, converted those to cards right there, and so you'd find the cards that need to be replaced with the correct code, retype those, put them back in the stack, put them into the machine, wait another 30 minutes out there. But each iteration was about 90 minutes, I would say, every time you corrected your code. I think most of you figured out that if every time you had a typo, if you had to lose 90 minutes of your life, how painful programming would be. And I'm sorry, but students here tend to think that programming is painful, right? You don't like programming out there. Just imagine if you were using punch cards and every mistake was 90 minutes lost out there. It would take you 4 weeks to do a 20-line program. I had some 30, 40-line programs that took me 8 hours. Now I can whip out a 30, 40-line program in about 10 to 15 minutes. That's there. One is I've gotten a lot faster, but the tools have gotten a lot better. As the tools have gotten a lot better, we've gotten a lot sloppier in our design work. Right there. So we tend to use the pseudocode more than we do the flowcharts. The other difference is we have text editors to write our pseudocode today, which makes it a lot easier than drawing flowcharts. Drawing flowcharts were by hand, and we could see the flow at there. And the other thing, and probably the most important thing in this list, is that most people that are programming learn at a younger age and think like programmers quicker. That's where you're lacking that one advantage, that you didn't have programming when you were 10, 12 years old in secondary school. Right there, where in many developing countries, developed countries, they start teaching program at the age of 10 and 12. That's there. I know the UK, they actually have students using Raspberry Pi at 8 and 9. And writing programs, all that there. I'm teaching Raspberry Pi in the microcontroller course, and people are kind of scared of this whole idea of learning Linux. And they teach Linux in the UK at 10 years old. So it's really, so back in the days that I learned programming, DOS was not out yet. We didn't even have DOS, and that was a text-based operating system. So we've got a couple of these. We got the if, then, else. We've got the switch statement right there. The switch statement is used for multiple selections right there. We have iteration, which is the while and the for, the do while and the for statements. And so we've got 3 of those. So we've got if else, and switch. So we've got 3 selection statements, and then we got 3 iteration statements. So we got 6 different control structures we have to learn right there. And I think last Friday I was having this trouble with something about the air in this room causing my sinuses to close up there. I can't breathe again. C only has 7 of them, that there are 3 for types of iteration and 3 for selection. Those are up there. And then the last one is the exit point right there. One of the things that we have that they talk about is that we should have a single entry and single exit in all of our iteration or any control structure. So we go in one place. Here's a block of code, We come in at the beginning, we go out at the end. We don't come in the middle right here. And we don't exit the middle right there. Sometimes we'll actually stick a return in the middle of our code, but it's actually considered bad programming. But it just makes sense to do that there. So we sometimes break that there. So in figure 3 there, I didn't see figure 3.1 that there. Control statement flow charts can be attached to one another by connecting the exit right there. Again, we're not going to be looking at flow charts out there. So we use control statement stacking. Basically, that's how we go from one block to another right there. We exit one block right there. And we'll get into some of these by practice right there. Thus, any C program will ever need can be constructed using only 7 different types of control statements right there, combined in only 2 ways. So everything we need to do can be done with these 7 structures, is what it's saying. Right there. So the if selection, we've already did an example of that one. If a student's grade is equal to greater than 60, print pass. Right there. So in other words, so in other words, we enter the grade. If it's greater than 60, we say that the student passed the exam or the course right there. So the condition is true, print is that there. So if grade is that there. So that is the if selection right there. If the condition is false, the printing is ignored, and that there. Now, if we have an else clause, which is the next one, then we would put print fail. So either we print pass or we print fail right there. And we can add the else if right there. If indentation is optional, it's highly recommended, and it's emphasized in the structure. Now, newer languages require indentation. What they mean by indentation is I put if, and I'm just going to parentheses with a dot. That just simply means a condition. And then I put an opening bracket right here. I put some lines of code in here. I put an ending bracket right here. And then I start with my next lines of code right there. What this indentation is telling me is that these lines of code are executed if that condition is true. By indenting it, when I'm debugging my code and trying to figure out what's going on, I can see very clearly what's inside the if statement. If I don't indent it and put my code here, then it makes it very difficult for debugging that there. And if I'm really, really sloppy, I put the bracket here instead of here. And I put this bracket here, right there. I can't tell where it ends, right there. By putting the bracket on its line by itself, it's very clear where the else ends. Right now, I'm teaching Python as part of the microcontroller course. I don't know Python. I joke with the microcontroller class that I stay about 2 slides ahead of them once in a while as I teach the language. Python does away with the opening and closing brackets. These brackets don't exist in Python. It relies on the indentation to tell where the beginning and the end of the if statement is. So in Python, I would say if my condition, I indent right here. I indent right here, and then I stop the indenting right there. The language looks at the fact that I've indented those to tell where the if begins and ends right there. So the indentation is now part of the programming language. C ignores the indentation. It doesn't care about the indentation. But I'm telling you to put the indentation in anyway. And the reason you should do that is it makes your code easier to debug and troubleshoot. But another reason is as you get older, and unfortunately, I was your age once, and I got old. There's nothing I could have done. I went from 25 to 60 overnight. I went to bed last night. I was 25, 26 years old, and I woke up this morning feel like I'm 60 out there. And that's and that'll happen to you too. And during the process of that happening, and it didn't happen overnight. It happened over many years, but it happened so fast that you don't realize that the languages you use are going to change. We're learning C today. Next year, you're going to learn Python if you take the microcontroller course that I stick with the Pi. Then you're going to graduate and you're going to go working for a company that is going to use Cobra or Zebra or some other language we haven't even heard of yet. I'm making up. I don't think there's a language called Cobra out there, but or Zebra. But we'll say that the next language is called that. So, just a couple years ago, Java was the big language, and Java is now going the way of Python. So, we're starting to see languages come and go freely. I learned on something called Fortran, which was developed in the 1950s, and it took a long time to move from Fortran to BASIC. The BASIC, which is still around, but it's completely different. The language is completely different, way off the wayside. And then Pascal became the big language. And then C became the big language. And then Ada became the big language, and then Ada disappeared completely. Then Java became the big language. But C still existed in the embedded world. There used to be a language called COBOL right there. Languages come and go just like women's clothing out there. Now, not so much in Malaysia, but I grew up in the 1960s. The miniskirt was the style. Then in the late 60s, tie-dye became the style. And then in the 70s, it became the mod look. Then the 80s became the big hair look. I mean, styles came and go with women's fashion out there. Right there. And I know some of the fashions found themselves in this part of the world too. I doubt the miniskirt found itself in the Islamic community too much. But back in the 60s, the Islamic community wasn't strong in Malaysia, so the miniskirt may have very well found its way into the culture. But regardless, these styles come and go right there. And as these styles come and go, the languages change out there. So you're better off learning that there. So the indentation is optional. It's highly recommended. I'd say do the indentation because the next language you use may require it. That's it. So this is the if statement right there in its full glory right there. And it says up there, if grade is greater than or equal to 60, that is the condition. What's in the parentheses is the condition. So it's evaluated as either true or false. And if it's evaluated as true, then what's inside those brackets right there is done. Now, I have a tendency of putting the beginning bracket at the end of this line like he does. Some people put it on its own line. It doesn't matter where you put it right there. But the bracket at there denotes at there. And in C, anytime you see a bracket right here, you're going to have a closing bracket here. And everything within this denotes a body of code. Right there. So we have beginning and closing brackets all over the place. Right there. So anytime you have a beginning and closing bracket, it's treated as one statement right there. So if we have this if right here, right there, this condition right there, we have this closing that there, this is evaluated and everything inside this bracket. In this particular case, we only have one statement in that there. So it says if grade greater than or equal to 60, print F pass. Right there. Right there. Now there's only one statement right there. So I could leave that bracket out. So that beginning bracket here and this ending bracket are optional in this case because there's only one statement right there. Good programming practice is that you use it anyway, but it's completely optional when there's a single statement right there. So the decision, okay, this is, I don't think I've got these figures inside these slides, and I don't care whether I do or not anyway. But all he says is that in this particular case, grade greater than or equal to 60. That's inside of a diamond. True. There's our print pass. Right there. False right there. So all the flowchart says is we're going to look at grade if it's greater than or equal to 60. Then we're going to go to this branch right here. We're going to print pass. Otherwise, we're not going to do anything right there. So, but there, again, I'm not going to go through the flow chart. I'm not going to require it. Oh, I guess he did give it to me. Right there. So, right there. So that's all that right there. So, the decision has two flow lines emerging from it. One is true and one is false. Right there. The if statement is a single entry, single exit. That there, if we can envision 7 bins each containing their one of 7 types, and I'm not going to go through this one right here. And here is the else failed. In this particular case, right here, the code looks like this here. You'll notice that we placed the else command in here. Hey, that's working today. What's going on here? I can actually write on the screen and it works in the right place. Is they fixed something here? So this is evaluated as true, we print pass. If this is evaluated, if it's not evaluated as that there, so the opposite of true is false. So in this particular case, the grade is less than 60. We want to print fail. So we have the else. So if sex if sex equal male, then you do something. If it's not equal to male, then we have to assume it's something other than male. It's probably female in the most common that there. We do something else right there. So again, this statement has to evaluate as either true or false right there. This is what happens when it's true. This is what happens when it's false right there. Right there. So this is an if or. If this is true, we do this. Otherwise, we do this right there. And right here. Now, I've also seen this drawn this way where we have the diamond and we have our blocks here. And then we have some blocks here, right here. And then we go back together right here. So this is going to the left or the right, and then we come back together at this point right here. Sometimes you'll see them where they put the false underneath right there. So this is the if else right there. We've already done one, as I recall, where we say if grade is greater than or equal to 90, else if, where we cascaded else statements after each other right there. So this C uses conditional operator. This gets really ugly. I'm just going to put it up there and say, don't learn this. Don't try to follow this right now. This says put string, grade equal or greater than 60. If it's true, you put here. If it's false, do this one right here. So this combines the printf and the if then and else all into one line. Right there. Essentially, that there. It's ugly. It's shorthand. And that's what a lot of C++ is, that there, that type of stuff. But this is, we're going to do, we've got three parts of this. We've got the condition, followed by, with the question mark right here. That's the end of the condition. And then we've got the true part, and then the false part, what we want it to do. Not a very user-friendly right there. And one of the things you might want to, especially as beginning programmers, you want to keep in mind is when you write programs, don't necessarily write the shortest and the fastest and the most compact program that you want to write. You want to write programs so you can go back and remember why you did things. When I write this piece of code right here, when I write this piece of code, I don't care whether I know how to program or not. I know what that means, right? That there. If you know basic English, you have a clue to what that means. If you don't know how to write code, you may not be able to write it off the top of your head or know when to write it, but you know what that means, right? And you can go through and you can clean it up and correct it if there's a mistake. Let's say this particular instructor changes the passing grade to a 50. I know that this is where I put the 50, change that 60 to a 50. When I read that, do you know what that means? I mean, until 10 minutes ago, could anybody tell me what this statement, what this line means? No. Not there. So, it's just one of those cases that you really don't want to use. If you don't understand, if you look at it and you can't figure out what it means upon that, don't use that type of syntax right there. So, that's it. So again, second, third can be executed. This kind of goes into this right here. He's teaching that format. The nested if then else, and I'm probably going to, I've already gone that there. The if then else, we've already gone through this in the example, so I probably won't give you a program to do today. I'll probably give you one on Friday here, but right there. But there, this is the one that I had you do earlier. Right here, if it's greater than or equal to 90, we print an A, else we print a B, else we print a C, else we print a D, else we print a C right there. And that's our pseudocode. This is our, now I think the only thing I did is I put the ifs right here on the same line, else if right there, which I think he does here, right there. This is the format that I prefer for this right here. Right here. So notice that the brackets are missing. He did not use the braces on this one here. So he didn't put a brace here or a brace here. He didn't put a brace here and a brace here. He didn't put these braces because there's only one statement in each else or each clause. So the braces are not necessary. If we wanted to put 3 or 4 statements, then we have to put the braces in there. So as far as the C compiler goes, they're both equivalent. The latter is popular because it avoids deep indentation of the code. That's why I use it right there, because I personally do not like this. As we get more involved, this gets farther and farther to the right, and you start running out of space right there. And in reality, this is what you're doing right there. Because we're looking at this grade, then we're looking at that there. So I prefer the latter of the two right there. Expects only one statement right there. I already mentioned if you have only one statement in the ifs body, you do not need to include it in braces. I mentioned that earlier. If you have several statements, you need to have the braces right there. Sets of braces are, within a pair of braces, are also called a compound statement or a block. The compiler treats them as a single statement, but they're actually a block of code right there. And I think I'm going to quit at this point right here. And here he's showing it with the braces right there. So, that there. So I think this is a good place to stop right here. Yeah, we'll stop right here because then we talk about the difference between syntax and logic here as we're changing topics a little bit right there. So I'm going to stop here at page 44 right there. Disregard and 55 minutes.